Okay, I'm going to talk today about variational autoencoder-based synthetic anomalies generation for model selection. This is part of the work that we do in Questar. First of all, before I dive into details and technical details, I would like to tell you a little bit about Questar. So Questar is a merger of two main ingredients. So one ingredient is expertise in the automotive industry with a lot of experience working with large fleets of worldwide companies. We have expert engineers working for 15 years tackling very challenging problems regarding vehicle health. And recently we've combined together as one group which also has AI expertise with talented researchers that eagerly doing every day the work of solving very difficult questions. So, and our main goal is to move from the world of diagnostic, or what we call, the light in the dashboard, which we all see in the car when something is broken, to something that is more predictive and can utilize the large number of data points that is provided every second from a modern car. And our main goal is actually to save costs to large fleets and, of course, improving the car safety. So this is basically what is the goal of Questar. So moving to our topic that I would like to talk about today. So I will go through several things. First, I will describe in a nutshell what is anomaly detection, basically. Then and describe the modeling approaches for anomaly detection, and describe what is the model selection problem when we are talking about anomaly detection models. I will propose a solution that we are now working at in Questar, show some preliminary results, and discuss a little bit. So the project leaders of this interesting and challenging problem are the talented research data scientists in our team, Stas Barbanov and Sofia Kovalets, accompanied by Dr. Sasha Appelstein, which is our head of data science, and myself. So anomalies. So anomalies can be defined in various ways. Let's stick to this following simple definition that says that, generally speaking, we have a normal distribution, a normal module of the data that is generated from some distribution P of n, Pn, okay? And we say that a point is abnormal if the probability of being generated from Pn is not likely. So it's below some threshold tau. So here we see, for instance, two modules of two modalities, sorry, for the normal data N1 and N2. And we have some outliers here, O1, O2, and O3, that are outside of this distribution, and we can call it anomalies. So this is very, of course, a simplistic description of anomalies in 2D when the dimensions are much higher and things are getting much more complicated. So what is actually anomaly detection modeling? So we have a model that obtains a point xi and gives back a score, okay? So a scalar. And we say that if the scalar is above a certain threshold alpha, we say that this point is an anomaly. So, and the anomaly detection pipeline includes both the scoring model and the threshold. And the scoring model, of course, can be trained in unsupervised fashion or semi-supervised or self-supervised, and or any other way you choose. There are many of them to choose from. And of course, there are other ways to calibrate alpha. It can be hard thresholding or some dynamic approach, or even a model itself. And so, as I said, we have enough to choose from, but the main problem is how do we know that an anomaly detection model actually works, okay? So we usually do not have access to enough or any real anomalies. So this is by definition, okay? We are trying to find something that is very rare or doesn't exist at all in our current data set. So this problem is limiting us in the possibility to give a feedback whether our model can provide precision or recall and AUC values that are reasonable or what we expected, or in a certain level of a false positive rate or a true positive rate. We actually do not have a way to calibrate the hyperparameters of the model to the task of anomaly detection. Okay, so we can calibrate it regarding the self-supervision that we apply, but we cannot calibrate it with regard to the anomaly detection task. And of course, adjusting alpha is also is the same as calibrating the hyperparameters, is a challenging task where we don't actually know what would be a good threshold for the score. Okay, so a common solution that is used many times is fitted by synthetic anomalies. So the scheme goes as follows. So first we generate synthetic anomalies by several ways. So some of them might be adding noise. So here we would we have a problem of oversimplified modeling of normal and abnormal boundaries. So it might be too easy to identify the anomalous points. When we are talking about shuffling, so sometimes it might produce still normal points or too much abnormal, and it is very hard to calibrate, and we actually do not know whether these abnormal points truly reflect reliable anomalies. And other approaches, more advanced, could be, of course, generative models, where we take the normal data and do some magic and provide new abnormal points. But unlike these pictures, usually GANs and others are struggling to make a real anomalies that truly differ from the normal data. And then after we generate these synthetic anomalies, we evaluate a model. So we can apply some cross-validation scheme with normal data and these synthetic anomalies, hopefully to get reliable feedback regarding our performance as the model M performance as an anomaly detector. But as I said, the problem is that we don't really know how to calibrate these anomalies in a way that we can rely on them as a good feedback for our anomaly detection models. So our solution, our proposed solution is VAE controlled synthetic anomalies. So we have two basic goals here. Okay? So the first one is to provide a reliable feedback. In examples such an evaluation metric F1 score, okay, which is correlated with the true labels if they were given to us. So we don't have labels, we don't have true positive anomalies, but we want to generate synthetic anomalies in a way that will provide us some hint of how the models will perform on real anomalies. So we want to have some correlation method. It could be Pearson correlation or other metrics, ranking metrics, which sometimes that are sometimes used, for instance, in commander systems. And the other goal is to support K-based model selection procedures. So it relates to one, but we want eventually we want to say that from these K models that we found out that perform the best on synthetic anomalies, some of them, or at least one of them, is good enough to be an anomaly detector. And this can be utilized for, again, model selection and also for a part of a pipeline of AutoML of anomaly detection, which is something that we want to explore further. So how the scheme looks like. So we have the sensors data that are coming from the car. We have lots of them. So many time series coming from what is called a canvas, which is a protocol for obtaining the data from several computer units that are spread around the engine. So we get a lot of them in high frequency, sampled with high frequency. So we get those time series and we ingest them to a variational autoencoder. So variational autoencoder, in a nutshell, is a way to encode the data to latent space in a way that this latent space is smoother, more complete, and is more, ordered in a way that points that are generated between the true points have true meaning. Okay, so the closeness in this latent space has some meaningful reason to be there. Okay, so for this reason we use the variational autoencoder. So we reduce the dimensions of the ingested points. So for instance, if we ingest an input of length of 100 and we have 40 features, so we have 4,000 points, then so we reduce the representation of these 4,000 points to a much lower dimension. And this is what is done here. And then we perform on this latent dimension representation, we perform an anomaly, clustering scheme for it could be k-means, dbscan, constraint k-means, whatever you can think of. And afterwards, in the meantime, we also generate anomalies based on the true data in a way in one of the ways that I've just described in the previous slide. So we have those two things. We have the clustered data, clustered normal data, and we have the anomalies that were generated. And the main thing that we do here, the most important thing that we do here is we apply a filtering scheme. And by filtering, we decide which anomalies do we want to keep and which we want to remove. So we can decide that we want anomalies that are more challenging to identify. So they are a little bit closer to the normal points. or we want to have generated anomalies that are quite significant, so they are very far from the normal points, or we want to decide to have a blend of those two. So here we can apply a filtering scheme. And the filtering scheme, again, can be in many ways, but we decided of the distance of each anomalous point that we generated from the center of each cluster, okay, that we just generated here. So we can filter and say that we want only anomalies that are within a certain distance from the closest cluster, okay? And this is the way we control the strength of the anomalies. And then when we have the anomalies, the synthetic anomalies that we filtered, we can apply any evaluation scheme, cross-validation, etc., and calculate evaluation metrics. So this is the general scheme that we apply. And as I said, we have a unique blend of engineering, automotive engineers, and AI capabilities. So we decided to utilize that for an experiment that is actually quite nice, that's supposed to reflect a true situation. So we took a real vehicle, Iveco Daily, and put a recorder in this vehicle, and this recorder is recording in 10 hertz sample rate many features of the engine. So it could be the RPM, the engine torque, engine fuel rate, gas mass flow, engine take, manifolds, etc. So here we had 20 features. We could have more, but for the sake of this experiment, this is what we used. And then our engineers enabled us 5 modes of this vehicle. So one would be the normal mode. Everything works as expected, and the car is okay. And 4 abnormal modes. So so the engineers actually intentionally made these fault modes. One would be leaking injector, other the disconnected injector, blocked air filter, and intake manifold leak. So these are, I'm not an expert in automotive yet, but these faults are usually not easily identified by by the lights that we see in the dashboard, and usually it takes time to identify them. And when you identify them, it is too late. Okay, so it's something went wrong, and the damage occurred to the car engine and other systems or other systems of the car. So it is very important to identify them in advance.
Okay, Yuval, I'm going to have to kindly interrupt you and say that we have a few more minutes before we have to open up to the floor. And we have some questions ready and waiting from our guests. So if we can quickly wrap up the Q&A, that would be wonderful.
Yeah. Okay. So basically, we used here as a clustering, we used the DB scan. We applied 8 anomaly detection models. Most of them are RNN-based with different configuration. And the synthetic anomalies were generated by shuffling. And we see here the result of one run of this anomaly generation. We see that most of the anomalies are out of the, in red, are out of the blue points, which are the normal data. And we see that some of them are closer and some of them are far away, but usually they do not overlap, only in some very specific cases. So this is basically what we wanted to achieve. So a realistic picture of how anomalies look like in reality. And looking at the performance of those 8 models on true anomalies, which we have now, and synthetic anomalies, we see that most of the time we are actually correct regarding the performance of regarding the prediction of performance of anomaly detection models. Unlike only one model here is an outlier in our retrospective. So, and we think we know the reason for that might arise from the variance of this model. And we see that generally speaking, we see that the correlation between the F1 score of the synthetic anomalies and the true anomalies is 0.7, which is nice to start with. So to summarize, so we propose a feedback scheme for anomaly detection using synthetic anomalies. We use a low-dimensional embedding space and remove undesired generated anomalies that are not relevant. As a result, we got correlated feedback from our synthetic anomalies to the true use cases. So that's it. Thank you.
Thank you very much, Yuval. That was very thorough and interesting. We had some questions coming in as you were talking. The first one, and I'm going to read, from my parenthesis limited experience, sometimes a point that is as far away as 3 SD units from the mean is still valid and not an anomaly. For example, even though the average age for a heart attack is approximately 60 years, there are cases of heart attacks in babies. How do you deal with these kinds of data points?
Yeah, so this is a great question. So the question here is, how do you separate outliers from anomalies? This is quite challenging, and one way to deal with that is to look at so for instance, in this place, we see that some points, blue points, are within the anomalous points, and it is quite challenging, and you have to identify the weaknesses of your model when dealing with these such anomalous points that are actually outliers and not real anomalies. I totally agree that there is a challenge here.
Okay, thank you. I suppose I have another question, which is, can different anomaly generation techniques be utilized in the pipeline that you propose? Well, and if so, how?
Yeah, so of course, so what I propose here is a generic scheme. So you can use any clustering algorithm that you want to, you would like to use, or any latent space representation, or any anomaly detection scheme. So it is a generic framework to apply for anomaly detection feedback.